Hello and welcome. It's been a while. This could be the first. This is the first live code stream from a shipping container in Arizona. But I used to code more, so this could be a resumption of that practice. Regardless, let's proceed. We are coding today on a HackerRank problem. Let's see this window here. All right, counting sort 1. So comparison sorting, where you compare elements, has a lower bound of n log n. It says quicksort usually has a running time of n log n, but is there an algorithm that can sort even faster? In general, this is not even possible, which is what I meant by the lower bound. But most sorting algorithms are comparison sorts. They sort a list just by comparing elements to one another. A comparison sort algorithm cannot beat n log n. For more details, you can look at these notes. It's probably a research paper. But there are alternative methods to comparison. So instead, you can create an integer array whose index range covers the entire range of values in your array to sort. What does that mean? Okay, well, if you have 1 million integers, the range of indexes is from 0 to 1 less than 1 million. But then the integer values themselves have a range, and they're saying that the values is comparable or is the same as the index range, 0 to 1 million. So it says each time a value occurs in the original array, you increment the counter at that index. At the end, you run through your counting array, printing the value of each non-valued index that number of times. Okay, so you have, let's draw it out, just because everything is easier to understand whenever you're drawing. This is not more than a picture is worth 1,000 words. This is, you become smarter if you draw. Most people, I think this is a saying by, if it's not Feynman, something Feynman would have said. So if you have an array which keeps track of counts, and then you have your original array, which has numbers, whose indexes range over the count. So you have the array of counts, and it's incremented at index I whenever you encounter the value I in the array, in the input array. We'll call it the input array. And then this down here is the input array. So let's say you encounter the value 100, and well, I guess it presupposes that your array of counts has indexes from 0 to at least 101. Let's say it's the range from 0 to 200. So then at the location of 101, which is right next to the location for 100, you would increment let's give it some line depth. Okay. So at 101, it's 0 by default, and then here it would be 1. And then, 0 by default everywhere else. Okay, and then, you're going along and you encounter you know, 173, and then likewise you increment that by 1. And let's say further down the line you encounter, 101 again, so then you increment to 2, and then, yeah, so that's an illustration of the range of the input array values matches the range of the indexes of the count. So you keep track of these two arrays. And then when you're done, you simply, so what is the sorted array? So the output array is, you go through the array of counts, and then you output for each. Let's see, how do I increase this? There we go. Okay, so the output array, what's the algorithm for that? Well, you go through the array of counts. You can ignore the input array. So go through array of counts, and for each, and at each index, repeatedly populate the output array with the appropriate number of copies. So that means you skip over most of these indexes probably that have 0, and then when you come to one that's non-zero, you repeat it that number of times. So you repeat the output array here. Let's say it's 0 over until 101, and then you repeat it twice. So then the first two values in this array are 101 and 101. Oh no. That got sent to the back for some reason. Or maybe the color got sent. Bring to front. Well, that is way too light. Okay, let's try again. There we go. Okay, and then you go through, 0, 0, 0, and you come across 173. So then that's the sorted value in the array. And this is a very simplistic example, but you get the idea. So before you had this array where you had 101, 173, and 101, which is unsorted, mildly unsorted. And then when you output it, you sort it in correct order, 101, 101, 173. And, it's a lot of overhead for 3 numbers. You could just sort this by yourself. But the important thing is that this approach is scalable. So if you had 1 million or 1 billion numbers, especially with a range also on order of 1 million to 1 billion, you can, this will handle that no problem. And then we can also talk later about what is the running time complexity or space complexity, which we probably will for HackerRank. Okay, so back here, you have an example, 1, 1, 3, 2, 1. And you start out with you have to create, array of counts, what they call a result here, which is of equal to the range of the values. It may not be as long as the input array, but it has to be as long at least of the array of values. And even though it says 1, 1, 3, 2, 1, it's telling you here that the values could include 0. So that's why you have 4 instead of 3 here. And so as you go through the array, I tracks the position through the input array. So you're considering index 0, because computer scientists always have to be different and count from 0. And, more efficient. Squeeze out the last value in your encoding. So this is the values of the array, 1, 1, 3, 2, 1, at index 0, 1, 2, 3, 4. And then the result, as it's updated each time, it goes to that value in the array of counts and it increments it. So you only see these values, monotonically non-decreasing. So they could stay the same. They could increase, but they'll never decrease because you can't unsee a number once you've seen it. So at the end, you get 0, 3, 1, 1. That means 1 occurs 3 times, which we verify here, 1, 1, and 1. 2 occurs once, which is here. 3 occurs once, which is here, and 0 occurs 0 times. So then to sort it, what do? You go through each index and you repeat that index the number of times the count tells you to. So you repeat 0, 0 times, you repeat 1 3 times, 1, 1, 1. You repeat 2 1 time, which is 2, and you repeat 3 1 time, which is 3. Okay, and so they want you to return, it says here to return the frequency array. So you don't have to return the output. Yeah, like this is the frequency array. This is the array of counts. This is not the sorted output array. And so the range is from 0 to 1 less than 100, so not inclusive. And then the array could be as long as 1,000,000, from 100 to 1,000,000. So that is our challenge. I'm not feeling ambitious enough to do it in C++ this time. Let's, what do I feel like? We can do Python 3. Okay, so we write our code here, and then there's some testing code here. And the array is an array of integers. Okay, so we'll define the array of counts. And we can pre-populate with zeros. In fact, we probably should pre-populate with zeros from 0 to 100. And let's see, what Python methods exist? We'll pop out here to run an interactive shell. So I'm not doing any Google searches, which I think has questionable. It's usually against most honor codes to do a Google search, or some honor codes, especially on a technical interview. But it depends. Please ask your interviewer. If it's take-home exam, for example, they usually allow you to do Google searches. I know there is a range function. So for example, you could do range 100. And range in Python 3 is a special object in itself. It is not an array, but perhaps it has a toArray function where you can enumerate it all. Or you can simply maybe pass it in as a list. There we go. Okay, so then there's nothing called zeros in particular. Well, it'd be unfortunate if we had to go through this thing and reset them all to 0, but I'm not afraid to do it. So it could also be a list comprehension. That's probably the best solution of all. For I in range. Okay, there we go. So that's the one we want. So list comprehension, which we can talk more in detail later, is sort of a compact way of generating don't want to say programmatic because that it's not a whole program, but I guess formulaically specifying the values of a potentially much longer list in a compact way. So in this case, every value is 0. That's an expression, using some temporary loop variable. In this case, we choose our loop variable x. So this 0 here could be any expression in x, but in this case, it's pretty constant. A simple way to describe it, 0 for x in range of 100. So that's counts. And then we loop through the array, and we say, for I in our pirate array, we will the counts at that location I, we increment by 1. And then finally we return counts. And so this, let's see, returns counting sort. Well, this is kind of counting sort implies it's sorted, but we have only been asked to output the frequency array. So let's try that. And we have no test harness. I'm just going to run it and see. It passed the test cases, so that does look like a typical output. And so I'm just going to submit it. Okay, great. Let's see, do I get a star or anything? I do. I got 100 points. It seems like a lot of points to get. But again, this was difficulty easy. So let's, there are multiple counting sorts as well. There's counting sort 2 and 3. We'll pause here and I'll check to see what the next problem is. Oh wait, I don't think you can pause a live video cast, can you? Well, all right, let me check on my phone. It's a good thing to, when you are broadcasting and you need to consult potentially private information, have a phone. It's a good technique. Okay, great. The next one is called, it was counting sort 1. That was the one that I was requested to solve. And the next one is called flipping the matrix. It's probably this one. And also some other users that have, by the way, if you're curious about my profile, it's not, there's no safety harness. I'm just sort of solving in real time. I make mistakes. I don't pass all the certifications that you would think I would pass after all of this time, or that you might hope that I would pass after all this time, but there it is. It's a real life, warts and moles and all. So 49 points to get my next star. That's very attainable. Okay, Sean invented a game involving a 2n by 2n matrix where each cell of the matrix contains an integer. He can reverse any of its rows or columns any number of times. Sounds like a fun game. The goal of the game is to maximize the sum of the elements in the n by n submatrix located in the upper left quadrant of the matrix. So let's kind of visualize that, because I'm a visual person. So you have a matrix, which is 2n by 2n. But you only eventually want to maximize the sum of the one in the upper left quadrant. So you're allowed to, flip any of the columns and then quadrant. So, it suggests that you might want to move away low-valued items, low-valued columns and rows to be these other quadrants, and then sort of swap in high-valued columns and rows here. So this is the quadrant that's n by n. And then you want to maximize, I think it said the sum of each row, and then also the sum of the column. Let's check. Sum of all the elements. Okay, not of any row and column, just adding them all up together. So that's good to know. Yeah, and let's say, you want to, pairs of numbers that are, let's say in the ith row and the jth column, and you want to, we'll write this as like an objective function. If this were like linear programming or any kind of, matrix filling operation, matrix filling business or company that you might have. So maximize sum of the rows from 0 to n, the columns from 0 to n, and the matrix element, which we'll write as big M at location I through j. So, by convention, the row is the first index and the column is the second index, but it doesn't really matter in this case. Just loop over both of them. They're both n. It's a square submatrix, and you want to maximize that. And we'll probably have a nested loop, right? You go over every row, you go over every column. That's n times n, so you'd expect kind of an n squared complexity solution, and that's probably good enough. We'll see. So you have a matrix, and yeah, this fits in nicely with Python syntax, maybe some other languages, where every matrix is actually a list of lists, which is, you could be a list of rows, or a list where each row is a sublist, or a list of columns where each column is a sublist. It looks like in this case, the rows are the sublist. So this is a list of rows. Yeah, a list of lists where the sublist is a row. And then we want to maximize the one in the top left, which is just 1. And 4 is the greatest number, so we rotate 2, 4 to this side, and then we rotate the row 3, 4, or 4, 3, I guess in that case, up above. And that's it. Okay, and so Q, they are saying, what are the constraints? What are we promised here? N is the size of the matrix, where 2n is the big matrix and n is the submatrix. So that's 128 inclusive. And then Q, what is Q? The number of queries. What is a query? So for the input, it says each of the next 2 n lines contains 2 n space represented integers. Okay, so that's the whole matrix. And then the first line of each query contains an integer. Oh, I see. So they're sort of querying, they're going to make you solve multiple of these problems. It looks like. Query is a strange word for it, but I guess they're saying you're going to have batches. So this is Q equals 1, but they could ask you to solve, 2 of these puzzles, in which case you would have, n equals 2. So 2n by 2n is 4 by 4 matrix. So if Q had been 2, you would have been followed with another set like this afterwards. Let's see if they give you, no example of that. Well, it's not that hard. If we solve it once, we can solve it multiple times. Let's see, this is the main entry point function, and so it is processing the input for you, which is nice. So they take out Q, and then they iteratively solve Q by calling your function, which is called the flipping matrix, and the result. And let's just make sure that the format of the result is the flipped matrix and not, some intermediate result that leads you to it. So, the maximum sum. Okay, there. It's good that we checked. So it returns the sum of all the elements itself. So not this flipped matrix, but this sum here. Well, let's talk about brute force strategies, or naive strategies at first. And the optimal solution is it doesn't ask even for the minimal number of flips, which would be challenging. Minimal number of swaps of columns and rows. It just asks for the final maximum. So you could go through the whole. You could sort, for example, if you had a sort. Well, that's a good question. Let's say you could sort all of the rows to have maximum values on the left. And then you could sort the columns to have maximum values at the top. And then that would be it. Then you take the submatrix in the upper left and you sum all the elements, and that would be the maximal sum. But the question is, can you create arbitrary elements? Can you create an arbitrary submatrix here given just flips of columns and rows from the big matrix? That is, can you always move two numbers? Let's say we want to move 83 independently from 101. Could you move them with enough column and row flips to be, to move 83 anywhere in the matrix that you wanted and 101 anywhere else in the matrix independently? And so the argument in that example is probably yes. Let's say you want to move 101 one column to the right and leave 83 where it was. Could you do that? Yeah, actually, could you? They would always be in the same column if you swapped columns. So I don't, and then, so you could move them rows relatively independent of each other, right? You could remove 101 up a row and down a row just by flipping these two columns or these two columns and leave 83 the same. You could flip 101 and 83 itself, but the only way to move them to a different column is to move them both together. So, so the initial approach, I think, will not work. Will be another heuristic. Heuristic is like a rule of thumb, sort of a compact rule, which is not guaranteed to be optimal, but is maybe easier to understand and implement. So we could go row by row, and well, you can't sort the rows independently, right? You could still sort the columns as you go down each row and then resort them as well. So what would that look like here? We would move 119 column here and then 112 here, but then you would also move the whole column. So in the rows beneath, these would travel together as well. So enough talking. Let's see if we can draw what that would look like. But I wanted them side by side. It's a different desktop. Oh, Mac. What have I done now? Well, this is part of the learning process is when you move a window accidentally to another screen, how do you move it back? Other than closing. Okay, hopefully that'll make it easy for us to find it later. So yeah, definitely don't create any passwords while live streaming your broadcast. Okay, here we go. So let's start out with the move that I had in mind, which is moving the column 119, 49, 43, and 108. I'll probably need to flip the columns later, so I'll just type them as separate numbers. And a little bit bigger. And this may not be the way they did it, but if it's not, we'll learn something. We'll refine our intuition, or we'll discover their own mistake. So then, 112 is the second column, and that's followed by 56 and 15 and 62. And then 83 is next. Underneath that is 56, 101, and 114. And last is the column starting with 42, with 125, 78, and 98 underneath. Okay, and then, so we've sorted the columns now. Let's see if that's good enough. For then, let's see, so for this row, next, 125 is over here, and it would be preferable for it to be in this column. And yeah, that does present a difficulty. How do we keep the 119 and 112? I mean, we could swap them down a column, right? Like swap these two columns here, the 112 and the 83, and then the 119 and the 83. So the effect is to shift them over by one, and then to swap it with this column so that it ends up over here. But this is becoming increasingly sort of case-based, sort of ad hoc than general. So the initial approach I thought where you go through and sort the columns row by row to maximize the value. That may not be the worst, but maybe we can go through and pick the biggest value. So if you go through the whole array, and let's say you say that 125 is really desirable because it's the biggest, what are the moves that move it to the top left? And then maybe you take a submatrix approach. So 125, if we move it to the top here, that's a swap of these two columns and then a swap of these two rows. What would that look like? So we'll move this up. We'll group this as a row as well. And then we'll ungroup them. Maybe someone will write a magic square web interface. That's my request to you. If you're in the audience, this is too easy. You need more of a challenge. Write me a magic square web UI, and then we can prototype matrix operations on it together. Okay, we've got about 14 minutes. Let's see what we can do. Okay, and then we want to swap these columns. So ungroup. And then regroup. Life is a sequence of groupings and ungroupings. Wait, does 56 really appear twice? It does, okay. Interesting. Patterns you discover when you arrange it. Oh no, I've inverted that instead of moved it. That is not an operation we're allowed to do. Reflect left to right. Okay. So now we have 125, and it's pretty desirable. Does that mean that we don't have to count anything else in the same column or row, and we can continue optimizing this submatrix, not including it? Well, that would only give us the biggest elements on the diagonal, but and that may work in this case just because it happens to be that 125 is in the same row or column as sort of like it's more of diminutive elements. But overall, I don't think that would work. Like we would want both 119 and 112, and they're in the same row. So, but we don't ideally we would like some sort of guarantee where once we move an element into place, we sort of never move it again. That doesn't mean we can't, how do we keep the top left element here? Well, that means after we've, moved an element there, this is row 0, column 0, that we never swap column 0 or row 0 again, but we could swap, row 1 and row 2, or column 1 and column 2. Yeah, well, let's continue. So we can only eliminate this as the biggest element. What's the next biggest? It's 119. Is there a way to move 119 over into the submatrix without disturbing 125? Well, no, I don't think there is a way of getting that over there. And even in the original matrix over here, yeah, because these are linked by column and also linked by row, well, I'm kind of stuck. Sometimes that happens. It seems like we can't. Yeah, we definitely can't manipulate the items automatically or individually. So what could we do to move all these elements, which are over 100, over to one side? Yeah, so for example, we can't have all three of these in the left submatrix. We have to choose between 125, 119, and 112, and these two. And of the two, we definitely should choose 125 and 119. So 112, unfortunately, will end up outside of that matrix. And likewise, 101, because it's not in the same column as 119 and 125, will be excluded. But together with 114, they form a pretty sizable coalition. So these two probably could end up in the upper left submatrix convincingly. That would be a strong claim for these two to be so first we could consider all pairs and rows or columns to be considered. For example, we'll take row-wise pairs. So there's a pair of 119 and 112. These other pairs are probably not in the running. Other row-wise pairs that are compelling, 108 and 114, is pretty compelling. And then for these others, 101 and 178, since that'll be less than 200, and then 125 plus any of these will also be less than 200. That would be enough for their rows. For each row, we could sort of list. This is kind of a dynamic programming approach where we have an intermediate results. The array of counts in the count sort problem before was also kind of that approach. So, 119 plus 112 is 231. Let's expand our row, or expand our frame. And then here, the biggest result would be, 125 plus 56, which would be 181. And then in this row would be, I'm just adding the two biggest numbers together. So 179. And then for this row here, it'd be 108 plus 114, which would be 232. I think that's right. Is that right? No, I think it's just 2, 2, 2. Dismissed as coincidence. Yeah, it's 2, 2, 2. And then likewise, we could do the same for the columns. And then, we want to keep track of which of those, along with the maximal pairwise sum, we'll keep track of which pairs those were. So I don't know yet what we're going to do with this, but it's a start. So then, down here, 119 plus 108 is 227. Here, 112 plus 62 is 174. And then 101 and 114 together is 215. And then here, 125 plus 98 is 223. Okay, so if we were to sort these by the highest summing columns and the highest summing rows, we might choose these two rows together, and then within them, these two columns. Well, that's surprising. Yeah, okay. So let's say we choose these two rows, and so we swap them up here, and then within the columns we swap this one, the fourth one here. Yeah, so fourth row up to the second row, fourth column to the second column. And what would that give us? Well, technically it should give us the elements that led to the maximal sum by row and maximal sum by column. Now they will be in the upper left themselves. So that means the sum of those would just be well, you don't want to double count these, so let's just add them up individually, and I'll write them here. Let's see, so if you flipped this row up here, let's expand again. And we'll remove these other counts since they were not the biggest, so we can count them, discount them. Okay, so now you have this, and then it was the first and the fourth column. You want to move the fourth column up. So that means now, and we'll see how we feel about this as we're doing it, right? Because we're rotating away this 112, which doesn't seem like the most desirable, but you're getting in the 125. Oh, I see. So the flipping should probably not just be by the maximum of each row, but the elements that lead to it. So if, for example, the maximal was, column 0 and column 1, And this one also, maximal row includes column 0 and column 2. Column 0 seems like a keeper, but then you have to choose between these two columns here. And okay, so perhaps the columns and the rows have votes about whether they should be flipped to the upper left. And so maybe let's take an approach that's similar to the count sort one. You're always inspired by previous problems, for better or for worse. So for columns, we'll record the votes. Sorry, for rows, we'll record the votes here. So the vote for this row is well, I'm not sure what would count as a vote in this case. It is the most, but this is second most, so this row has, well, let's do by columns for row count. So this column here, there's a vote for there's a vote for 0, row 0, and row 3. So we'll start them as 1 here. And then for this column, we count increment this by count 2, and then add 62, which again is the bottom row. So again, it's looking good for row 0 and row 3. And for the next column, it's element 2 and element 3, row 2 and row 3, I mean. So this is a 1. So according to this metric, the last row is looking pretty good. And then for the last column, it's this row 1 as well as, okay, so according to this method, this is a really desirable row at the bottom here. And then the next most desirable one is the first one. And then we can do the same for, time is up. Okay, we'll stop for now.